Alright, so in the previous topic, we focused on momentum. Now we're going to look more at energy. So the first idea for energy is the concept of work. So the basic equation that you may have encountered in the past, work is defined as force times distance. Again, it's a little more complicated than that when we're looking at the three-dimensional world. There's usually an x, so like a cosine theta. So you need to think about for work to occur, the force and the distance covered must be in the same direction. So if we just look at these four scenarios to start with. If we are just pushing the object directly, if we are pushing the object directly to the right as seen in this picture, if we actually draw the free body diagram of that block, we know that there's normal force up, ground holding up, there's force of gravity downwards, we're applying a force to the right. So when we look at the normal force, work is force times distance. So this thing's not moving up or down. So that means the work done by the normal force is 0. The work done by the force of gravity is 0. But we are getting work done by that push to the right. So since the velocity is to the right, the force to the right, we're ending up with some positive work. And when we look at this next scenario, we're pushing downwards. So let's draw our free body diagram again. Force of gravity is down. We're pushing down to the right. And normal force is up. So again, assuming that the ground does not give way and this thing falls downwards, this thing is moving to the right. So we still have some positive work. In this case, we have the object's moving to the right, but we're applying a force opposing that motion. So Fn, so maybe that could, a more common that might be like a thing, object sliding and friction's opposing. In this case, we have that finger that's pushing back, force of gravity, and we're pushing backwards. So this kind of time we have negative work. Now if we're pushing downwards and the thing is just traveling to the right, the amount of work we are doing is no work. So Fn, force of gravity downwards, force applied, get no work. Now if we think of the equation, what is cos, right? If you remember cos from math class, cosine looks like this, right? So in this one, cos, the angle is 0 degrees, right? 0 degrees is just 1, right? So you just get that maximum force. And this one, we're pushing to the right, cos at some angle downwards, but we know that from math that cos is positive in those two quadrants. So we're pushing in those directions, we still get some positive work done. However, on this one over here, what's the angle? If the motion is to the right, that's a 180 degrees. Cos 180 degrees. That's equal to -1. That's why we have that negative work occurring. And for this last one, we end up with cos, what's that, either like 90 degrees, or if we had cos 270 degrees, both those are cases when our angle comes out to be 0. So that's why we get no work. So we scroll down to our first question right here. It says a 50 kilogram crate is pulled 40 meters along a horizontal floor by a constant force exerted by a person. Applied force 100 newtons, which acts at 37 degrees to the horizontal. Okay, let's just draw this out first. So here is our scenario. We have an object. This is very similar to dynamics actually, but now we're just trying to incorporate energy into it as well. So here's our applied force, 100 newtons, at an angle of 37 degrees. There's a force of friction opposing it. We know there's force of gravity, and there's normal force. So this one, I'm just going to give us the force of friction so we don't have to calculate it, but from dynamics, we know that we are able to calculate our force of friction. So let's see what happens. So the work done by the normal force, that's a 0 joules, because this thing is, we're assuming this thing's moving to the right. Okay. The work done by gravity, that's also 0 joules, because this thing's not accelerating up or down. But the applied force, work done by our applied force, Fa cos theta times how far it travels. So this thing, it's 100 newtons of force being pushed with or pulled. The angle is 37 degrees, and it's traveling a distance of 40 meters. So we end up with 3,200 joules. If we look at friction, force of friction times our angle times d. Doesn't matter if we put an angle before and after the d. Friction is 50 newtons, and it's actually acting at cos 180. So we don't actually, you can just go ahead and just put that negative in though, but that's where that negative is coming from. Times 40 meters. We end up with negative 2,000 joules. So the work done by U is 3,200 joules, work done by friction is 2,000 joules. So if those two numbers were equal to, like equal in magnitude, so if the work, if applied was 2,000 and friction was negative 2,000, what that means is that it's the speed of the object's not changing. But in this case, what you can see is our net force is actually positive. So our net force is, if I add up everything together, WA plus WF plus WN plus WG, we see that it has a net force of, net energy of 1,200 joules. So net energy of 1,200 joules. So what does that mean? Like, where did that energy go? So what this means is that as the person that's pulling it, you have transferred energy into the block. So by having a net positive energy, what that actually means is that this object is picking up speed. So if we want to take this one step further, we can say, what speed is this thing now traveling at? And we can do that by saying, by the energy. So work is just the change in energy. So work, that's just defined as the change in energy. So we think, if we think of this as equaling to like changing our kinetic energy, 1/2 mv squared. So we say 1,200 joules is equal to 1/2. Mass is 50 kilograms. V squared. If we now solve for V, what do we get? So we got 1,200 times 2 divided by 50 square root. We see that the speed of this object, V is equal to, in those 40 meters, has changed by 6.9 meters per second, because we've added more energy to the block.